Greetings, aspiring scientists. Welcome to today's video. Today I'm just going to continue my previous topic on 3D Lewis structures and just do a couple of practice questions today. And I should keep it to that, so this video shouldn't be too long. So let's go to my slides. Okay, so practice. Deduce the electron domain geometry and molecular geometry of each of the following, then draw an appropriate 3D Lewis structure with approximate bond angles labeled. Okay, so a lot of things to do, but keep in mind that you only need to draw a 3D Lewis structure if the geometry is actually a three-dimensional geometry. So things like linear, trigonal, planar. The difference between a regular Lewis structure and a 3D Lewis structure is nothing, so just keep that in mind. So let's try this. So starting with A, NF3. You would draw your normal Lewis structure. But here we want 3D, so I'm going to draw the lone pair and one fluorine in the same plane, the plane of the screen of my tablet here. Now I have two more fluorines, so one of them I'm going to make dashed line, and the other will be wedge line. Just color that in. Okay, so this is the 3D structure of NF3. You always need for a tetrahedral electron domain geometry, which this is. That's part of this question as well. This is tetrahedral. Two things in the same plane that are attached to the central atom. So I'm choosing the lone pair on the top and the fluorine on the right. They're in the plane of this screen. Then the other two fluorines, one goes into the screen, the other comes out. So what is this molecular geometry? Again, this has the formula AB-3E if you use that system. So that is in fact trigonal pyramidal. Same as ammonia. Okay, is there anything else that must be done? Approximate bond angles. So the normal tetrahedral bond angle is 109.5. But when these things battle, these electron domains battle for which pushes which one's going to win? If you watch my previous video, you'll know that the lone pair wins. It's going to push everything closer together. And when it says label the bond angle, it means usually the F bond angle. So this must be less than 109.5. You can label it just like that. Okay, that's good. Then you don't need those little arrows I wrote on the top. I'm just trying to show that this lone pair causes that bond angle to be less than 109.5. Okay, so that was A. Let's do B next. Clear this. BF3. B, draw your Lewis structure. F. Oh, one thing I realized I forgot on the previous answer there. Those fluorines should have lone pairs just like I'm drawing here. So I'll just draw A quickly over here with the lone pairs. If you're technically drawing a Lewis structure, you got to have all the lone pairs. Okay, it can get a little bit messy with all these dots, but then back to B here. So the boron in this doesn't have any more electrons, no more lone pairs. It doesn't have an octet, but there's not enough electrons to give fluorines and boron their octets. So fluorine being more electronegative, they will get their octets. Boron is stuck with 6 here. That's fine though. But this is just AB3, so this is electron domain geometry, trigonal planar. And molecular geometry, also trigonal planar. And if there's nothing messing with these bond angles, they're all going to be about 120 degrees. All right, that's good. Then C. C is HCN, so we'll have a central carbon. We'll have a triple bond to nitrogen with a lone pair, and then a single bond to hydrogen. So this geometry, we're looking at the carbon in the middle, electron domain geometry, linear. There's two domains, a triple bond and a single bond, no lone pairs. Molecular geometry is the same, linear, no lone pairs on that central carbon. So there's no 3D structure for this, just like in B, no need to draw dash or wedge lines. And approximate bond angle here, 180 degrees. That's as far apart as pairs of electrons can separate. Okay, easy if you can remember that Lewis structure, triple bond, single bond. It does come up fairly often. HCN. Alright, NH4 plus, feel like we've talked about this a lot as well, so I'm going to choose two of these H bonds, make them in the plane of this screen. Another one, dashed line, another one, the last one, wedge line. Don't forget that positive charge, so this needs to be in brackets. Or at least positive charge labeled on the nitrogen. Okay, shouldn't be any other lone pairs, but we need the angle. When there was a lone pair, this was trigonal pyramidal. But now that lone pair is gone, and everything is equal and symmetrical again. So this molecular geometry has actually gone back to tetrahedral. So we're just going to have the one bond angle. Well, all four are the same. This angle of 109.5, the standard tetrahedral. I'll just make that a little more clear, 109.5. Okay, tetrahedral, positive charge. That is D done. Next, ECH2Cl2. So we'll start with carbon in the middle. This will be tetrahedral, carbon bonded to four different things. So you need to just choose two that are in the same plane. Maybe I'll choose the hydrogens, draw them. Then the next one has to be dashed or wedged, Cl with its lone pairs. And then wedge for the other one to show the opposite direction, 3D, Cl with its lone pairs. No charge on this, so that's fine. Now, geometry, electron domain geometry, tetrahedral, molecular geometry, also tetrahedral, no lone pairs on that central atom. What about bond angle though? So this is maybe something I haven't discussed much in my previous video. I talked about double bonds have more electron density, they'll push away single, triple even more, they'll push away others, lone pairs even more, they'll push away others. But what about if we just compare atoms here? Which one do you think would push away the others? A large chlorine with 3 lone pairs and a single bond, or a tiny little hydrogen with a single bond? The chlorine is going to have more repulsive power to push away things. So I think we're going to have a small angle HCH less than 109.5. And probably we're going to have a larger than 109.5 in between CLCH angle. I don't know exactly how much, maybe a couple degrees, but that should be fine to indicate. Okay, that's my guess anyway. F, let's try that. BeH2. So will this have any 3D components? No. This is just one domain on each side of beryllium, no other lone pairs. This is linear electron domain geometry, linear molecular geometry. Just two domains, no lone pairs going on, so this angle should be pretty much 180. Okay, that's easy. G next. OH minus. O, gotta have at least one single bond to H for these to be connected. Then where do the rest of these electrons go? It's this oxygen, gonna have 3 lone pairs, and it's received an electron. So that makes this negatively charged. So what geometry is this? This is also maybe something we didn't discuss in my previous video, but it should be fairly obvious. Think outside the box a bit. If you just have 2 points in space connected by a line, what angle are we talking about? Well, there's no angle really. It's just a straight line. A straight line has like a slope of 180 degrees if you consider the angle that you'd have to go around to reach the other point. I guess it's not a slope, but angle around a circle to reach the other point is 180. So this is on the oxygen IB-E3, not a geometry we talked about, but something you can consider. This should also be tetrahedral electron domain geometry, because that oxygen has 3 lone... Sorry, my mic just fell. That oxygen has 3 lone pairs and 1 single bond. What's the molecular geometry then? As I said, that is actually linear. Where the bond exists, it's just one bond. So, I mean, if you really wanted to try to draw the geometry of these lone pairs, you could do what I have been doing. You can put one lone pair in the same plane as this bond, and then try to draw the lone pairs with wedges and dashes. You do see this sometimes, and they'll often be drawn with wedge and dash attached to these lone pairs, and maybe like a little orbital showing that. You do see this sometimes. Okay, a little bit tricky. G, and then finish with H. Okay, HNO2 minus. I think we've done this before in my Lewis structure video. So this is going to have a double bond on one side, single on the other, extra electron on oxygen on one side, and lone pair on the central nitrogen. And this whole thing is negative charged. So do we really have to consider 3D for this? Not really. This is going to be a trigonoplanar electron domain geometry. Molecular geometry, we have a lone pair. This is an AB2E system. So it's not trigonoplanar, but this will be V-shaped or bent 120 degrees version. Okay, it's 120 degree version, but this lone pair will push the other bonds further away from it. So this angle is going to be actually less than 120, maybe 117 or something. And that's the angle that we need to identify. So that should be all these done, A to H. Hopefully you got some good practice and insights on to when things need to be 3D or not, how to include the dashes and wedges, how to predict bond angles. If not, there's plenty of other resources in textbooks and online. You can check it or ask me if you have any questions in the comments. So I think we'll end the video here for today. I do plan on making another video today, maybe top 10 most difficult HL topics for chemistry. If you're interested, check it out. And thanks for listening. See you next time.